taking the limit of this. Now, when you guys go to take a limit, make sure that you guys always test it. This is the limit as x approaches 2. And so if we wanted to find that limit, what you would do is you just plug in the 2 to all your x values and see what you get. So if we plugged in 2, we get 2 to the 3rd power minus 8. And on the bottom, we would have 2 to the 4th power plus 2 times 2. And we subtract 20 from that. Let's see what we get. On the top, that's going to be 8 minus 8, which is 0. On the bottom, 2 to the 4th is 16. And then we would add 4 to that, which would be 20, right? And then we would subtract 20, which would be 0. So we got 0 over 0, which is indeterminate form. So you would have to do some form of manipulation or whatever with this to try to find the limits. Now, because we know derivatives now, we can use L'Hopital's rule, which is taking the derivative of the top and the bottom, and then finding the limit of that. So I take the derivative of the top, I get x or 3x to the 2nd power divided by. And I'm going to take the derivative of the bottom, so it's going to be 4x to the 3rd, and then plus 2. The constants go away. And since I'm just finding the limit of this thing, I just do the same thing that I did before. I plug in the 2. So we're going to plug in 2 here. We got 3, 2. We square that. We get 4. 2 raised to the 3rd power. We add 2 to that. So we get 12 on top. And on the bottom, we get, what is that, 8. 8 times 4 is 32, 34. And we could simplify that to be 6 over 17. That is our answer. You can use L'Hopital's rule whenever you get an indeterminate form of 0 over 0. And actually, there's another case. If you get an indeterminate form that is infinity over infinity, you can also use L'Hopital's rule. So these are really important right here. I mean, if you would highlight something or box something, those are the things that I would make sure I know. You have to have a 0 over 0 or infinity over infinity indeterminate form in order to use L'Hopital's rule. Now, I am a very visual guy, so after I do this, I naturally graph it because I want to see if it really does work. Okay, so here's the graph of that function. Here he is right here. Looks kind of funky. Has this little bump right here. Now, what was the limit approaching? 2. It was approaching 2. Does this right here look like it's about, what was that? Yeah? Bless you. Hey, it is undefined right there. That's a hidden hole. That doesn't look like 6 over 17? 6 over 17 is really close to 0.5, isn't it? What's half of 17? It's close to 0.3. What's half of 17? It's 8.5? Yeah. So 6 isn't almost half of 17? It's less. It's a little less? So doesn't this look like it's a little less? Yeah, it's a little more than 0.3. Isn't that a little more than 0.3? If I look right here, this would be 0.5. That would be 0.25. It's a little more than 0.3, so it's right. It says it's undefined, but that's the value of the function. We're finding the limits. Okay? All right. So let's go back to this. Let's do the next one. So what you do right here is you plug in the 2 just like we did before. So we go 4 minus 2 squared. On the bottom we have sine, and that's going to be 2 pi because the x is multiplying times the pi. And I like to put the parentheses, but most of the time the book will not put parentheses. If the things are multiplying, the numbers are multiplying right after the trig function, you have to assume that they're both inside the trig function. So we have 4 minus 4 up top, which is 0, and on the bottom we get 0 because sine of 2 pi is 0. So we have 0 over 0, we have another indeterminate form. So we take the derivative of the top and the bottom. So I'm going to write the notation like this. I'm going to take the derivative of the top and take the derivative of the bottom, see what I get. So the derivative of 4 is just 0. The derivative of negative x squared is going to be negative 2x. Then we have the derivative of the bottom. Now don't forget, whenever you have things inside of the trig function, actually almost every trig function, just always do the chain rule. Okay, so let's do the derivative of sine first. The derivative of sine is cosine, so we put cosine, then we put pi times x inside of cosine. And then we have to multiply this by the derivative of the inside. So what's the derivative of pi x? Just pi. Yeah? Pi is like a constant. And normally, I guess another way to write this would be to not put the pi right there, because if I put the pi right there, I got to use brackets, because I have to say that the pi is multiplying the cosine. You could put the pi in the front, like that. So it would be pi cosine of pi x times x. So now we're going to find the limit as x approaches 2 for this one. So we do the same thing. We plug in the 2, and we get negative 4 on top. And what we get on the bottom? If I plug in 2 right there, that would be cosine of 2 pi. What is cosine of 2 pi? It's 1. So we have pi on the bottom, and that would be your answer. Nice and pretty. Can one of you guys go negative 4 divided by pi? Tell me what you get. I want to see what this is approximately, so we can, I like looking at the graph. What is it? Negative. It's got to be 1.
Negative 1.27.
27. Okay, let's see our graph. It's this one right here. I already have it up here. Okay, so here's our graph. Right here, that's our function. Now we're approaching 2. So what is that? Does that look like negative 1.27? About? Yes. And I'm guessing there's a hole right there. Yep, there it is. Wait, I missed it. There it is. There's a hole right there. It is undefined right there. That's why we had to use L'Hopital's rule.